we're not talking about cooking too much. We're talking about materials, but it's cooking because we're using heat. So, okay. So first of all, overview of what we do in my lab. We synthesize 1D nanocarbons, more specifically carbon nanotubes. We have over 15 years experience in synthesis of carbon nanotubes. We worked also on graphene derivatives, graphene oxide, reduced graphene oxide. I'll present a little bit about it. But mostly we focus recently on transition metal chalcogenides. And we have a technique where basically we produce bulk layered transition metal chalcogenides, and then we and when we can top down deposit them, drop cast them, sonicate and drop cast them on any substrate. So the key piece of equipment in my lab is this, and we have two systems very similar, where basically we have two tube furnaces in series. So this is you have those two tube furnaces, and I want to spend a little moment with you because this is a very important slide, where basically this system is extremely versatile to synthesize low-dimensional materials. So how does it work? We have those two furnaces. One we call it preheating, where basically we condition the precursors in here. And one is called synthesis, where we put basically the substrate or the material we want to react, and the catalysis happens in here. And what is important is, since those two systems are decoupled, we can control independently the two temperatures. So for example, for carbon nanotubes, we put a substrate in here and we flow gases containing, for example, carbon and hydrogen, etc. When we do metal chalcogenides, we put a foil of metal here, and here we introduce a powder, for example, of sulfur or selenium or phosphorus, and we sublimate and we control with the flow and with the temperature how much will be the reactant meeting the metal foil and forming this. And all this, of course, is done under a hood for safety because we don't want to breathe any of this stuff. And with this, we have been successful in synthesizing 1D and 2D materials. Of course, once, for example, if we have bulk layered materials, after that, we can sonicate and disperse, or we can use them either as flakes or as bulk for electrochemistry, more specifically electrocatalysis or photocatalysis. That's what we do in our lab. But we collaborate with many people to do devices, or to do composites, or to do other applications. So first, let's start to do the 1D research. So in the happy carbon family, one of the prominent members is carbon nanotubes, which can be viewed as a rolled sheet of graphene. Usually carbon nanotubes come into flavor, single wall nanotubes or multi-wall nanotubes. What I will present here will be based on multi-wall carbon nanotubes. And I don't have to expose this, but I think that you all know carbon nanotubes have amazing properties. So first of all, they are the closest structure to a 1D, ideal 1D, very, very thin, nanometer size diameter, and can be very long. So the aspect ratio could be in the millions. And there's no other material that has those properties. Has high electrical conductivity, can be very strong, is inert, but can be functionalized, very high thermal conductivity, has been used for field emission, etc. It has amazing set of properties. So a lot of scientists have investigated a lot of things to do with carbon nanotubes. I will focus on the synthesis. Once upon a time in the 90s, people were growing entangled, short, micron-long carbon nanotubes, and that's what I call spaghetti. They look really like spaghetti. And we also did some of them in my lab, and then I always challenge people, you see this 6 carbon nanotube in the shape of 6, if you can do this, I'll invite you for dinner. Then in 2004, the group of Kenji Hata innovated in introducing in the reactor parts per million of water vapor in conjunction with ethylene, and they were able to show the growth of millimeter tall carpets of carbon nanotubes. And that was a quantum leap for this. We did our incremental innovation on this. And this is where you see, for example, the value of having the two systems decoupled in the furnace. Instead of having parts per million of water, because when I did my PhD, it was very expensive to buy a control system for that. So I thought, maybe we can mix hydrogen and oxygen and get the water there. And that's what we did in the first zone. So by playing in the first zone, in fact, I had the 3-zone system during my PhD, we can combine the water vapor here, controlled by the limiting reagent, which is oxygen, which is basically an argon tank with a 1% oxygen, and then react in the third zone and do the magic. And in fact, we showed how by introducing only 10 standard cubic centimeters per minute of argon with 1% oxygen in there, so a very tiny amount of oxygen, right? It's 1% of 10, 0.1 SCCM. We increase the growth of the carpet by a factor of 10. So how to grow carbon nanotubes? This is what I call the carbon nanotube synthesis for dummies. Is basically you take a silicon wafer, you put on it by beam evaporation a layer of aluminum oxide, let's say 10 nanometers. On top of that, a nanometer layer of iron, which is the catalyst. You put it in the furnace, you heat it in the presence of a reducing agent like oxygen, and that dewets the film and forms those dots. Those dots will be the nucleating sites for the carbon nanotube growth. So at some point you introduce a carbon precursor, can be ethylene, can be camphor, can be benzene, can be whatever you want that has carbon. We use ethylene. And then by crowding, since every nanotube could grow in any direction, but if the density of active catalyst is high enough, they all push each other, and at the end, by crowding, they will grow on the way up. And this is how you get the carpet of carbon nanotubes. And what is fascinating here is you have many, many interesting complex physical chemical phenomena like chemical vapor deposition, surface chemistry, the thin film reactions, different mechanisms, gas phase reactions. So there's plenty. There are a few inputs we can control and very few outputs that we can control. And sometimes those outputs are interrelated one to the other. So now let's go advanced level synthesis of carbon nanotubes. I use this metaphor of planting. When you want to plant, you need three elements. You need the seed, you need the soil, good soil, and you need the rain, the nutrients, the sun. For carbon nanotubes is the same thing, but we call them with fancy terms. The seed is the catalyst, the underlayer is the soil, and what we call preheating is the rain and the sun, the conditioning of the precursors that come in there. This was my first work, was basically, here we have our system of iron and aluminum oxide. You see the model is in here. And basically, if we heat it in the presence of hydrogen, which is basically annealing. So if we anneal it for increasing durations, as you know from material science, you'll start coarsening. First of all, you'll de-wet the film if it was continuous in the first place, which is not sure because it was very thin. And then eventually you get some coarsening. When you get coarsening, it means your dot becomes larger. If the dot becomes larger, since it's the nucleating site of a nanotube, your nanotube will have a larger diameter. So basically the iron catalyst is the father of the nanotube. And so by controlling the diameter of the iron catalyst, by controlling the annealing duration, you can control the nanotube diameter. And we showed that basically this is for increasing annealing times, you have this S curve of the average diameter of the catalyst dot, which is a typical of coarsening. Very nice. That's one way we can play with the iron catalyst. Another way we can play with the iron catalyst is we can change its oxidation state. Iron is a very funny material, has something like 16 oxidation states. We usually use 4 of them. And here we're able to control the oxidation state from Fe2O3, Fe3O4, FeO, and Fe. And basically, we show how the height of the nanotubes depended on the oxidation level of the catalyst. So basically, we can control the catalyst oxidation state also. That's another technique to control the height of the nanotubes. We saw 2 too far. Now, I will skip on many other examples. We can play with the underlayer. I'll show you something later. But what if the catalyst and the underlayer are the same? For example, a stainless steel coin. So we were able, as others have done, to grow carbon nanotubes on stainless steel coins, and we use them for some electrochemistry. And we also use them, this is in collaboration with Professor Kerry Pint, by growing carbon nanotubes on a stainless steel mesh, we could do structural composite supercapacitors. Now, let's look at the preheating. Let's look at the nutrients that come there. What happens if I change the preheating temperature? So here is, I changed only the preheating. I did not change the temperature of the substrate. I wanted to grow at low temperature carbon nanotubes, and I changed only the temperature of the preheating. And we see that there is a clear change in the height of the nanotubes with this system. And basically, if we plot it as an Arrhenius plot, the mechanism, we see that the mechanism is very, very different. And what is very interesting is that the slope of this curve corresponds to the activation energy of iron also. So it's a very interesting phenomena here that is going on. So with the preheating on, we can grow taller carbon nanotubes without increasing the temperature of the catalysis. We also noticed that the structure of the nanotubes improved by increasing the preheating. And we try to analyze with ex situ GCMS what kind of compounds were responsible for the best nanotube growth. And we found out that those were interesting. And it's interesting because some are, fluorantine, for example, has a 5-member ring and 6-member ring. And there was a work in the old times about the growth of mechanism of carbon nanotubes starting from the cap. And to do a cap, which is semi-buckable, you need also 5-membered rings. So maybe those are really nice, compounds for having crystalline carbon nanotubes. But this is all speculation so far. And we pushed the system even further. We had a study a few years ago where basically we tried all kinds of combination of preheating without changing anything on the growth. And you can see this is carpet height as a function of all those different combinations. Go and look at the paper if you're interested in what they are. And basically we can see that how important the preheating is, and it makes massive difference. So now the new challenge, everything I showed you so far was about growing carpets of carbon nanotubes of a certain height. But what if I want to modulate the height? Well, this has been done already. Work from John Hart and work from others to do MEMS. Basically, you can do photolithography and liftoff of the catalyst. So very nice. But the one thing that you notice on those nice motifs is that there is only one height. So it's either nanotubes or nothing. How about having different heights? Can we have different heights of nanotubes? The group of John Hart showed something very interesting a few years ago, where basically they changed the underlayer, what is below the catalyst, and they were able to have different heights, or even by differential growth to have those curving structures of carbon nanotubes. What we did was different. We noticed, for example, in this piece of work that was where basically we wanted to grow carbon nanotubes on copper. Why? Because that's useful for electrical application. We wanted electrical conductivity. But what we did, since it doesn't work iron on copper because of interdiffusion and other phenomena, and copper is a killer of carbon nanotube growth, we put in between the iron and the copper a thin layer of aluminum oxide of 10 nanometers. And we were able to grow very nice carbon nanotubes. They were crystalline, everything was nice. Now the question is, I said I wanted electrical conductivity. If I put aluminum oxide in there, there will not be any. And in fact, we measured some. And we wondered, why is this conductive? So maybe the aluminum oxide layer cracked and has some defects and allows contact between the nanotubes and the substrate. No, the alumina layer is pretty good. What we noticed instead that was fascinating and that triggered our thinking was that while the nanotubes originating from the iron catalyst sitting on aluminum oxide were growing happily carbon nanotubes, from below, from floor -2, copper was diffusing into the aluminum oxide and doping it and making it conductive. So interestingly enough, we see that maybe that we can have an interaction between the nanotube growth and what is below the aluminum oxide layer. So we developed this model, which is the same as before, but you notice here we added one piece. We call it reservoir. What if we have a thin film reservoir below the underlayer while we do the growth? Can we affect what's going on? And the first thought was, why don't we put iron? Why iron? Because one of the theories of why carbon nanotube growth stops, and we cannot grow more than a few millimeters or centimeters today, up to today, is because the iron diffuses into the aluminum oxide, and that's game over. But what if we replenished from the bottom? So we tried, and very interesting, we always obtained much taller carbon nanotubes when we had a reservoir, sometimes factor of 2. So that was very promising. And the problem was that when we tried to have different thicknesses of aluminum oxide, we noticed some weird things. So if the aluminum oxide layer was 10 nanometers, we saw some of those big boulders here. And if it was thinner, we saw many more of those boulders. But if it was thick enough, no boulders appeared. So we noticed also that the kinetics with the reservoir was way faster. And we also noticed that there was no coarsening when we had the reservoir, contrary to what happens in a normal system. So we wonder what's going on in here. Finally, what gave the kicker was, if this is the growth with the reservoir and the alumina layer of 10 nanometers was twice that of no reservoir. But the one when we had the alumina layer thick enough, let's say 30 nanometers, then it was comparable to the original sample. So basically, from that, we postulated the mechanism based on pinholes. So what happened was that the iron diffused to the surface via pinhole diffusion, and then affected the dewetting of the iron layer, forming thinner, smaller iron dots, and usually smaller iron dots grow taller carbon nanotubes. So that was interesting. So we thought, oh, great. So we doubled the height of nanotubes. Can we maybe kill nanotubes? And we did it. We used here a layer of an alloy of copper and silver below the aluminum oxide. We know that copper is the killer of carbon nanotubes. We added some silver. Why? Because copper and silver is a eutectic phase diagram. So we lowered the melting point of the alloy, and therefore we speed the diffusion. And in fact, if you look here, without reservoir, we have a growth that depends on the growth duration. And with the reservoir, we have zero growth. So by patterning, remember, we patterned 2 floors below, right? Not below the catalyst, below the catalyst. And we were able to obtain those patterns replicated in the growth of the carbon nanotubes. And basically, is the fast diffusion of this alloy that goes to the surface, poisons the iron catalyst, and doesn't make nanotubes grow. We pushed it one step further, and we said, what about putting another material under that? Let's try moly. And moly was even better than iron. So we can have much thicker, much taller carbon nanotubes with a moly. And what was also interesting was that the moly thickness influenced the height of the resulting carbon nanotube carpet, which was not something that we noticed with the iron. So bottom line, we have now a whole array of materials that we can use as reservoirs to modulate the height. And the dream is, if someone can do this, or some collaborators here are interested in extensive photolithography capabilities, and if we could pattern different materials at the reservoir level, meaning 2 floors below the catalyst, then we could have, for example, different heights of the carbon nanotube. You want to do a mounting, for example, or you want to do something that has a third dimension. So now let's go into the 2D research. 2D research, we started with graphene oxide, and we found a way. This work shows that by reduce graphene oxide further by an annealing at high temperature in hydrogen, we can increase significantly the conductivity. So that makes it a material that is extremely interesting. We also showed that we can use chitosan to dope, but I want to focus on this. There are many families of bulk layered materials, what we call the metal chalcogenides, for example, or the oxides. And there are thousands of them. And it's very interesting because each material exhibits different properties, especially band gap, for example, mobility. And when you think about this, then you can play at the Lego, like a Lego structure, my favorite toy when I was a kid, and build heterostructures where you have conducting layers, semiconducting layers, insulating layers, and do very original heterostructure with properties that we haven't seen so far. And many people are working on this very exciting field of research. We started using it more in electrochemistry. They're very interesting because they have specific catalytic activity. They're very suitable for intercalation, and they can have also very different types of crystal structures. They're very interesting for electrochemistry. How do we synthesize them? So this is the same as the system before. Here, the gases are coming from the right, just to confuse you. And we have a chalcogen, basically a powder, for example, of sulfur or selenium or phosphorus, that we introduce into the furnace at a certain temperature, T1. And then, so the temperature is to modulate their vapor pressure of the sublimation of this powder that will reach the substrates, which are, for example, metal foils on the furnace two at a different temperature than the first one, and do the reaction here. So this is the formation of the reagent, and this is the catalytic control. The first work we did was on digenite, copper 9, sulfur 5, and basically we saw it was a very interesting material that had those grains, a unique stoichiometry, and it was 2D layered. We could drop cast flakes. Now, one thing that was fascinating was that despite the band gap of 2.5 electron volt, it was more conductive than germanium and silicon, which makes us think about the defects that are into this material. And we showed also that it could be a decent electrode for lithium-ion battery in collaboration with Professor Noquet here in Ilan. We did something similar with silver sulfide, but this is an electrochemical water splitting with Professor Zitoun. And then recently, I want to show you, just to conclude, two works on tungsten, metal selenides. Why metal selenides? They're less explored, and they're very interesting for many different applications. And also, the crystal structure can be modulated very specially. So this work is about tungsten selenide. One thing that is fascinating in all these syntheses is how do they grow? What's the mechanism of nucleation and growth? And it's extremely, extremely complex. So what we do, we analyze growth at different stages for different durations. We do extensive characterization at HRTEM, HRSEM, etc., and try to learn from it what is the mechanism. And this is the fascinating part of it. And also the crystal structure, we show that we can exfoliate and drop cast flakes. And this system, besides this, has been used also in collaboration with Professor Comini in Brescia to do sensors. Although in this paper was about electrode for lithium-ion battery with Professor Noquet again. And finally, another example I want to show you is, for example, silver selenide. This is with Professor Schechter. We did oxygen reduction in alkaline medium. And we have many other works. I don't have the whole list in here of metal chalcogenides we're working on for electrocatalysis and also for photocatalysis. And I would wish, if you are interested, to expand into even other areas. So just to conclude this, if any of the materials that I showed are of interest to you, please let me know. Those are bulk 2D layered materials. Or are you interested in new, different materials that we could look if we can synthesize, or are you interested in collaborating to form some composite materials for new applications? So bottom line, I showed you a menu of 1D and 2D nanomaterials, and I believe they are very important materials for future applications and devices. This is my fantastic, varied team. And of course, funding and amazing, amazing collaborators. This is only a very small list that allowed us to do what we have done. And for any question, you can contact me. My email is here at the bottom. Thank you for your attention. And if you have any questions, I'm here.